particles come later. The beginning is beginning is very soft, slow start. So group of persons who come later shouldn't worry much. So congratulations and with selecting this course as part of your curriculum, and I hope it will be a positive experience and you get some useful knowledge out of it. And to my memory, what my colleagues told that last meeting someone was talking to you about how the class went last time, and you got some general idea. So today I will try to combine first and second lecture in 1 hour and 50 minutes, and the first lecture that should be delivered last week will be very verbal, nothing challenging, some general words, and the second one will be introductory steps towards actual computational chemistry. So before we go to scientific part, I want to announce so that you get an approximate idea what to expect during the class. So I have notes ready for 27 lectures, and maybe we will shrink or expand some of them. And there will be some very easy homework which are not a substantial part. It is just to refresh your memory and my memory. And there will be an option for extra credit, and I will offer you to give presentations. So a couple of lectures will be devoted, not I'm speaking, but you will come here and talk and record it on this
Can you tell us why the sound
new facilities. And there will be a computer lab section, which is not in the schedule. Formally, officially, you are not required to do it, but it is your best interest to attend it, because we get some helpful practical skills that are not possible to cover in lecture. And I'm not sure if you need a midterm, only if you insist and someone tells, no, I want a midterm. So in the computer lab, we will start with doing some common assignment for everyone to practice our skills, and then after we accumulate some skills, we'll go to independent part, so that each of class attendee will do something unique. And then we can also discuss if you really like a formal final, or maybe instead of formal final, we will set up written reports and oral presentations based on the independent research project. So the class is not formal. You are welcome to make suggestions, to change the way we go on the way, and this should be a positive experience for everyone in the class, including me. So regarding the subject of the course, regarding the scientific, for the first hour, we'll just set up what will be our goals for the next 4 months. Compare what the difference of computational course compared to standard theoretical approaches like quantum mechanics, physical chemistry. So which objects do we study, and can we solve all problems in the world, or there are some limitations? And then just enlist which practical skills you expect to acquire during the course. So goal of any theory and computation is to support experiment, to be helpful. The amount of experimentalists is at least 10 times more than theorists, so theorists should serve to experimentalists to help them. And generally, one can reproduce experiment, predict outcome of experiment, or model some materials and some properties that have never been measured but could be measured in the future. So just help present, past experiment, and future experiment. And one can focus on different observables, just reproducing what is measured in experiment. And also there is a area one can apply both theoretical and computational skills is to try to predict, to suggest the ways how to build a material with desired properties. So, consolidating some ideas, one can maybe give some suggestions if someone need good light absorber or whatever good charge transfer material. Theory and computation can help. So why computational approach is better than theoretical? It is easier, so we need to think less and get more results, be more productive. The chance of success is much higher because if in real theoretical chemistry and theoretical physics, people work like 3 years for a single paper, they make errors and they correct them, and it is ever going process. And in computation, is a little bit quicker. In computational approaches, one can treat much bigger systems that are related to true real world, and in some very lucky cases, one can even reproduce specifically exactly model the systems that are treated experimentally. And also the benefit of computational versus theoretical, that one can treat some irregularity. Models and systems where there are no symmetry, where everything is shaking, waving, there are some defects, and it is not a problem for computational treatment. So it is a sweet spot where you can get experience, apply, and be very helpful to the rest of researchers, rest of scientists. So what computational chemistry does, one accumulates the theories and positive knowledge from this theoretical modeling into some software packages. And in the easiest way, we do not need to know what is inside. So we just need to operate it to provide input and process output. And in the a little bit advanced approach, we should know what is in these packages and which theoretical concepts help to predict properties of materials and predict some observables. So all of them solve some equations in a numerical form. We save time on solving equations. And here, here are necessary practical steps that we do. So we provide input and take output of the software packages. Okay. So which theoretical concepts do we need? Are there a lot of them, or they are more simple and generic? Well, all properties of materials, if you want to be precise enough, are based on quantum properties of electrons moving around some atoms, forming bonds, being responsible for optical properties. So every modeling starts from Schrodinger equation, and then there are several either extensions, making it more complicated and more precise, or simplifications, making it a little less precise but more applicable. Practical, from practical side, we need to play with the concept of atomistic models. So if we describe some molecules or some semiconductor models or metals, any materials, we need to represent a material as a set of atoms. And to specify, we need to be specific, we need positions of atoms and their actual which element of them. And this setting up positions of atoms is not a big scientific challenge, but practically it is an important step, and it is unavoidable. no one can help us in most cases, and it needs some additional skills to build atomic models. In some rare cases, if the systems are periodic, we can ask the help of our XRD expert, or if you know how to operate this machinery to get coordinate from there, but it is only in very rare instances. So here are the list of possible observables that one can extract from modeling, and the list is very long. One can there are much more observables that are possible to compute, that those are too challenging and not possible. So one can start with stability of a model, chemical stability of a model, the geometry, the bond length. So those are practically most simple things. And then one can go to electronic properties that are measured in the electrochemistry. One can reproduce UV visible spectrum, or at least try to reproduce for different compounds. And one can make an attempt and be successful to estimate an ability of material to create charge transfer states, to absorb light, form new compounds, and those all things are going in the quantitative way. Well, what are major limitations? Can we solve any problem in the world, or it is still a limited approach? Well, there are two sorts of limitations. Number one is size of the model, because our computers are not big enough, and some of the programs do not scale, do not parallelize well. So, you know, the basic idea is that if you take very big system, then you take million of computers and ask them to communicate with each other and work cooperatively. But some computers are not quick enough. Well, generally, they're not unlimited. And second thing, there is, for some algorithms, computers do not want to work cooperatively beyond some threshold. And there are those two objective limitations tells us that we cannot take more than, let's say, 1,000 atoms for electronic properties. If we need only positions and some geometry with reduced precision, one probably can go to like several thousand atoms or even million atoms, but no absorption, no electronic properties, only position. Another challenge for computational chemistry are excited states, because if a computational chemist approaches an experimentalist and say, I want to help you, I want to reproduce your observables, the experimentalist tells, how precise? Are you going to reproduce my results with 5 significant figures? And most likely no. And though this question of precision is especially sensitive for excited state, when the model is prepared in the non-equilibrium state, when some electrons, some excitons are created, then precision of all methods is decreasing, and there is a lot of activity in attempts to design methods that produce better and better precision. But there is a compromise. If you go for high precision, it takes too long and you cannot take bigger systems. So it is always a fight between precision and computational limit, the time limit. How can we verbalize it? Precision versus the resources. Well, um, there are also many areas of purely scientific and applied research that currently use help of computational chemistry. And in case you are interested in the job market, I know that pharmacological, medical industry is very interested in computational chemistry experts because just very basic prediction of the structure of molecules is helpful in drug design. The electronic industry is really employing a lot of computational chemists and material designers to predict the properties of all these transistors, integrated schemes,
Something is wrong.
developing multi-layer solar cells. And one of the best areas to apply computational chemistry from my personal view is anything that is related to light harvesting, photovoltaics and photocatalysis. So it has a very good combination of applicability of methods, amount of some unresolved problems scientifically, and chances to success. But there are much more other applications. So what are we going to do as independent projects, and which materials we are going to use for training? So we should respect the profile of our department and the research project that we are involved in general. So it should be some materials chemistry and photoactive nanomaterials, photoactive nanosystems. So we will, in our training, we will try to select such materials that are photoactive, that are nano and small, and we hope to apply skills that we get in class in our future research. Yeah, here is just a list of skills that I was trying to write down from the top of the head, and you should establish a way so that I communicate you the slides, because I'm lazy to read all this long list. So let me just go through section. So you will definitely, as a very basic skill, get some working knowledge for operating supercomputers, some environment of language of talking to supercomputers, giving them orders and operating files, which is very different from what you typically have on your Mac or PC. There, instead of operating with mouse, you type commands. It's more like talking to a person or to a robot. So then we need skills in molecular design, so either to extract them from XRD or build them by hand with some specific software. Then there is a list of some really simple basic computational skills of finding basic features of electronic structures, be able to reproduce, for example, electrochemistry experiment, like position of occupied and energy of occupied and unoccupied orbitals and things like that. And also, as time passes by, we will get to more.
Excuse me, Dr. Kilin.
Yes.
There is some problem with the sound. Your voice is not actually coming through all the time. I'm not sure why. Maybe it's because of the mic position, something like that.
Okay. You hear now better?
Yeah, I'm hearing it now better.
Probably there are some contacts here with the antenna. Is it better now?
Yes, it's better now.
It sounds good, yeah. It sounds better.
Okay, thank you.
Thank you.
So, there is an important feature of many objects that we are seeing in experiments and in the nature. They are experiencing thermal motion. A lot of models, a lot of actual systems do exist at room temperature instead of zero temperature. And it means that the position of atoms are not stable. They're not sitting at one place. They are shaking all the time. They're moving with some velocity. And this additional feature brings new set of observables, new set of properties that we will also address in the class and in the computer lab. And there are the most attracting thing is that if something is moving, one can visualize it and make movies. So we will make movies in our computer lab. Okay, I'm done with lecture number 1. If you really want a little break, we can do it, or I can keep talking. And probably, if I go with space, we can leave earlier. Okay. I will try to make adjustments to this new technology and learn how to provide handouts in electronic form without handing them out. And I was trying to upload a little document to the D2L. Have you seen it? Okay, I'll probably ask in an email. Can you see it or not? And we need to establish this technology so that we can share documents. So I have uploaded very little PowerPoint that I stole from or asked from someone that provides an opportunity to recall basic information about quantum mechanics, about Schrodinger equation that we are supposed to be aware of right now. And I'll try to design a little simple verbal homework to distribute next time and to ask you to return next Tuesday. But those are very little percentage of the course. This is more just for entertainment. So for doing our computational lab, I recommend you to think ahead about it and record this email. Douglas Genuine. It is a gentleman who is responsible for our university supercomputer, and he will be happy to open accounts on supercomputers for you. So it is a opportunity account, same as you log into any computer on the campus. There is a specific server that is disconnected from all other servers, and you need an additional username and password. And we will do practice on this supercomputer. In addition, we will make. Actually, it is already ready. There is a common username and password so that we can log in. Everyone can use, in addition, the same name and password so that we can see what other members of the group are doing, and it will be easier for me to supervise what is going on. But I'm suggesting that you get your own account too. So in this second lecture, we will try to realize how to convert from general principles and from general information about a material to very quantitative characterization of material. Which steps do we need to start precise modeling? So we will establish some strategic ideas, strategic plan. Then we will try to share our own vision, your vision, what is a molecule. Then we will set up some practical goals. can just briefly agree that we all know what quantum mechanics is. And then the biggest part of this lecture number 2 is establishing so-called molecular Hamiltonian. So generic Hamiltonian that will describe any molecule or any material with supposing that we put right numbers there. And then we will talk about, is it possible to simplify it. Okay. So you can draw this diagram, this empty diagram in your notebooks, and we will do it together. Yes, please. It was. Okay, thank you. So this diagram is supposed to describe all computational chemistry. Of course, in some simplified way, but it is what we will be doing or what a computer will do for us. So we start with this input with atomic models. And at the output, we get observables that we can communicate to our experimental collaborators, or if you do experiment, just to look on them and see if they match the measurement. Sure. And we do have something in between. How we get from atomistic model to the observables, to reproducing the experiment. So there are some generic theoretical concepts that are the same for theory and for computation. They typically start, it all starts from Schrodinger equation, but there are some more advanced equations. So theory, and typically it starts with Schrodinger equation. And all theories are consolidated into software packages. I'm saying really baby steps, really simple thing. So they are consolidated in software that is being running on computers, right? So we have software and we have a hardware. And usually they both are just bound together as a cluster with many processors. Like here on desktops today we have like 8 processors, and on supercomputer usually it is like few hundreds or few thousand, and they are arranged in a way to work cooperatively. Okay, so it is a summary of the whole course, if you like. And let me see how I did my homework typing it. Oh, okay, I swapped the theory and atomistic model. So you have atomistic models, you have the cluster, and you do have observables. And to build the software, we need some theories. Okay, please give me suggestions if there are volunteers who want to explain all of us what is a molecule. Can you switch on the mic for the?
I think it's combined between 2 atoms or more.
Okay, okay. If you want to be a little bit more precise, we should respect the idea that atoms are composed of ions and electrons, right? And those electrons sometimes migrate from one atom to another one. So it would be more precise to speak that we have 2 or more ions and 2 or more electrons, because sometimes we do not know if electron is attached to a specific ion, right? Any corrections, objections, other suggestions? Will we accept this definition? You guys have a background in chemistry, strong background in chemistry. So if you accept, you'll write it down. So molecule set of ions and electrons. And they probably are stick together, localized in space. Okay, very good. So if you want to speak about to model properties of some molecule, right? We need to specify the positions of those ions, and we need to match the type of element, number of electrons, and probably find where they are and what they are doing. So we are simply, with baby steps, going to quantitative description of any material. So the minimal goal in quantitative description of a molecule, quantitative description of a molecule, is to reproduce, guess, support the correct interatomic distance. It is not the whole computational chemistry, but it is like the very first preliminary step. Correct interatomic or interionic distance. Are you okay with this? And if you want the distances, we probably need positions of each ion.
Dr. Killen?
Yes?
One question actually, that is the interatomic distances is the output of the model, or initially we give it into the model and still it might be a little bit off, so relaxation
Yes.
and other things.
Perfect question. Yeah. Thank you. So you provide them as an input, and you get more precise interatomic distances as an output.
As an output. Okay. Thank you.
Actually, I've got a training in theory much earlier than I started computational exercises, and when friends of mine told me what it is, my first idea was that, oh, okay, you take a box, you put there randomly the ions from atomic composition, you just shake it and wait until it combines into right compound. Like
self-assembles.
It doesn't work. It will take same long time as it took evolution on the Earth. To be practical, one needs to do educated input. It saves a lot of time and gives results much quicker. So what do we do next? So we need to solve Schrodinger equation. We need to use quantum theory, and I assume that you all remember what it is. So Schrodinger equation is typically started with time-dependent form, respecting the fact that electrons are moving and the states of electrons are not constant in time. But for a lot of practical applications, one remove time dependence and solve so-called time-independent Schrodinger equation. And the major feature of this equation is that it has a infinite number of solutions. So the solutions are amplitudes of probability for wave functions, and each of the wave function has its own eigenenergies. And if you want to return back to time-dependent picture, one needs to specify initial condition and then superimpose different solutions with oscillating factors to get time-dependent solution. So if you have questions, if you want to revise this material, please contact me now or after the class, because here it is very squeezed, very condensed quantum theory course that takes a semester to absorb. Okay. Are you okay with this? More or less. Okay. So now let's draw a picture. So I invite you to draw it in your notebooks, and I will try to draw it on this facility. So we will draw a model of a simplest possible molecule. It will be a schematic, which will show all major features and will show a nomenclature to quantify everything in the atomic model. So probably the simplest molecule is H2, right? So 2 ions, 2 electrons. Or maybe 2 ionized helium. Well, everything else will be more complicated. So the lowest number of ions is 2. Well, one probably can assume H2 plus with 1 electron. But let's draw a model for H2, for neutral H2, where we do have 2 ions and 2 electrons. So we will use big circles for ions, and we will use small circles for electrons. And since we do want interatomic distances and we want positions, let's try to be really rigorous, as professional mathematicians are. If you want to specify a position of something, we need to establish a system of coordinates, right? So we need to start with an origin. And then we will specify positions in respect to the origin. Right, origin. Put some dot here, which will be like 0, 0, 0 in Cartesian. Then we are drawing 1 proton. We are drawing second proton. And we are saying, okay, this will be distance from the origin, well, not distance, vector connecting origin and first proton. This will be the vector connecting origin and the second proton. Now we do plot 2 electrons. And we specify, although we know that electrons moving like crazy with a fraction of speed of light, but anyway, we need to be precise. We need to specify the position of electron, at least in our model. So we connect the origin by a vector with an electron, and to we need to design a nomenclature. We can assume that just accept nomenclatures that since ions are bigger, we will use capital letters, and electrons are smaller, we will use lowercase letters. So it will be R1 lowercase vector for first electron, R2 vector for the second electron. And now I'm going to do 2 things. I do not know which one to do first. So I want to enlist all features, all characteristics, all quantitative characteristics of each particle in this area. And then I want to draw additional vectors that connect electrons to each other, electrons to ions, ions to each other. So probably let's just write down features of each particle in the list and then make the picture more complicated. So for ions, which we also can call nuclei, right? We can say that each ion has a mass. Also use the uppercase letter and index them with, I don't know, some mass. They have charge, capital I for ion. Okay. Then they have position. And also, if they are moving, we can assign a velocity or momentum of each ion, right? And we can do the same thing for electrons. Although electrons have the same mass and each electron has the same charge, but we want to be very specific, and let's complete the table. So mass of an electron, charge of an electron, position of an electron, and momentum of an electron. Okay, we did our first step towards modeling. At least we know what we are interested in. So, are you okay with this? I hope so. That was a really baby step. Now, we should recall that electrons and ions interact to each other. Right? So, the charges of the same sign repel, charges of the opposite sign attract. And this force between charges is proportional to the distance between them. Therefore, the interatomic distance is very critical. So they all are connected, the interatomic distances and electronic properties of the system. And also distance from electron to ion is important. And before we process further, we probably should make a mark on our diagram that we are interested in the distance between electrons, R1, 2, small. We are interested in the distance between ions, R capital, 1, 2. And we are interested also in the cross distances from ion to an electron. I don't know which letter to use. Probably just R1 minus R1 absolute value of vectors. Here R2 vector minus R capital 2 vector absolute value. And we also need the two more vectors. They will be looking ugly on this picture, but I will just make the dotted line. We need distance from here into there. So we need from first electron to second ion, and we need from second electron to first ion. So those all are parameters that will allow us to describe properties of a model. So there is nothing intellectually challenging, but it is boring to write it down if we want to understand the principles, how things work. But in practical steps, we will need really simple steps. We just making some intermediate work to understand what is going on. So why do we need these positions? Why do we need these forces and how they are connected to the Schrodinger equation, to quantum mechanics, and to observables and properties. Any ideas? So if we want quantum properties, we want to solve Schrodinger equation. And Schrodinger equation has a one important input. It is a operator of energy, the Hamiltonian. And in order to get properties of a material, we need to set up a Hamiltonian of our model. So for each molecule that we play with, we need a Hamiltonian. Hamiltonian of H2 molecule, Hamiltonian of H2O molecule, Hamiltonian of cadmium 1000, selenium 1000 quantum dot. So for each model, we need a Hamiltonian. And therefore, we need all these parameters because they will be helpful to establish a Hamiltonian. So let me verbalize it just for the record. So for Schrodinger equation, one needs a Hamiltonian. And our next step will be to take all these parameters from this drawing, all this list of features of electrons and nuclei, and feed them in, to use them to build a Hamiltonian. Okay, next simple step. The Hamiltonian is operator of energy. Right? And the energy typically has two components: kinetic energy of motion and potential energy of forces. So that's it. This is the idea. We just need to carefully implement it. And we have two types of particles. We have ions and we have electrons. And each of them can move, and each of them can interact to each other and to the particles of the opposite side. Therefore, we should just carefully write down a term that gives energy related to this mechanism. So we will have 5 terms in the Hamiltonian. So energy of motion for ions, energy of motion of electrons, and then energy of ions interacting to each other, energy of electrons interacting to each other, and then the cross term, how the electrons interact with ions. In the simplest, it is not simple, but in the model that can be solved theoretically without computer, in the hydrogen atom, we typically have only one ion, one electron, and we have kinetic energy of ion, which is supposed to be 0, kinetic energy of electron, and we do have, please come in if you are interested. He's not interested. and we have energy of attraction, Coulomb attraction between ion and electron. So in hydrogen, we will have only this. And this. So the molecular Hamiltonian is a little bit more complicated than atomic Hamiltonian. And we know how big pain is to exactly solve hydrogen atom. So it takes a lot of efforts. And here, well, for some simple molecules like H2, H2+, there were an attempts to solve them analytically. People were writing theories, writing like many pages equations and publishing them in 1930s. but in about 1950s, one has realized that one can use computers to solve Schrodinger equation and other equations numerically, and it is much less painful than trying to solve these complicated equations, and which are really not possible to solve by a human being for more than like 3 ions and 3 electrons. It is just limited. So how do we build formally the energy term associated with motion of something? What did you have in your other classes or in your high school science? Any suggestions? What is the kinetic energy of an ion? Do not hesitate, it is really simple. What is the kinetic energy of your car? If it has a big kinetic energy, it can heat well something. If it is less, it doesn't. Well, kinetic energy is ability to make some work to overcome some barrier, right? And it is bigger for heavier systems, and it is bigger for systems with larger velocity, right? C square if c is velocity, but typically letter c is used for speed of light. If you speak about some real material objects, you use letter v for velocity because it is smaller. M v squared over 2. In the simplest case, right? And or you can say that it is v squared over 2m, because v and p are connected, right? And I assume you all can write that. What is the connection? Yes? Okay. But here we have more than one particle, more than one ion. So let me cross it because it is not precise. And for actual molecules, we have many ions. The index, we label them with index I. It goes from first to ion number n. And then we have a momentum. You know, momentum is just mass times velocity of an ion, and squared. And the square doesn't affect even if it is a vector. It is fine. Nice arrow. And we divide it by 2m sub I, mass of the ion. So we have many ions. Each of ion is moving, and we have a energy contribution to the energy of the whole system from this moving ion. This should be a part in the Hamiltonian. So for moving electrons, it is completely the same approach. We just draw a symbol of sum, use some other letter, I equals from 1 to number of electrons, and we do E lowercase squared vector over 2m. And we do not need index because mass of each electron is the same. Here is a little note that we are going to play quantum games. We need the quantum properties of electrons, which are not actually, although we are speaking of the position of electrons, they are not particles. They are distributions in space. And therefore, instead of classical variables, we need operators. So in anywhere we write this p, we should assume that it is a operator like this. So it is a operator that acts on a wave function and takes derivative of it. I'm just skipping it to save space. But in quantum world, in one world, P is operator. I just put a hat to save that it is a P is operator. Are we okay with this? Objections? Questions? No. Okay. So we are done with energy of motion. Now we need to recall the Coulomb law. The energy of attraction or repulsion of charges, right? So if you have two ions, each of them has a charge, like I don't, well, for hydrogens it will be +1 +1, but if it is something heavier, ionized, it can be other Z number. So we have Z capital charge of ion number I. We have a charge of ion number J. We know that if it is a repulsion, right, it means that if you bring together some substances that do not want to bring together, if you make force, then total energy increases, right? So the contribution to the energy should be positive. We can bravely write a plus sign in front. And we can also bravely put a summation sign. Make summation over I and over J. And we also aware from our previous education, from our experience, that force and energy is stronger if we bring them closer and closer and closer, and it is maximal if they are really close. So it should be, according to Coulomb, inversely proportional to distance between them. Right? So those are natural ideas. So we have a distance from position of ion I, which is vector, minus position of ion J, the vector, absolute value. Any objections? Are you fine with this? Okay. Let's just repeat, practice calligraphy, and do the same for electrons. So they also they are charges of the same sign. They also repel if one tries to bring them close together. And the difference will be only in the nomenclature, and the letters will be lowercase instead of uppercase. We do this E, also plus sign, summation, lowercase I, lowercase j. And here we do, you do not need to write this Z numbers, it will be just -1 times -1, right? Charge of electron, divide by position of the electron number I minus position of electron number J. Okay, we are 80% done. We have 4 out of 5 terms. So we need the remaining one, the interaction of electrons and ions. Are you tired? Bored? We should become more energetic in the later. But those are important steps that we cannot avoid. So nothing intellectually new. We put a minus sign because positive and negative charge attract. So as closer they are, as more energetically favorable it is, right? So the energy decreases if you bring together opposite charges. Minus since favorable. So it is minus sign. Then we have a plus Z sub I capital for charge of ion, and then minus 1 for an electron. Oh, if you have a minus from here, then we do not need a minus here. We already have it. Then we have a summation, and here we do two indices. One index, capital index for ion, and then lower index for electron. So I capital, I lowercase. If we divide this all onto R sub I vector minus R sub I lowercase vector absolute value. Okay, great. We did a good job. We are jumped from hand waving and general speculations to the language of quantitative description of material. We didn't got any positive results yet, but we are already on the way. We have started and we know what we are doing. I'm going to switch to next page, and if you have any objections or corrections, tell now.
I have a question, Professor. This 4 pi epsilon naught, are you purposefully eliminating that?
Yes, yes. We are going to accept the atomic system of units. Thank you very much for this very relevant question. So for atomic system of units, U, in which mass of electron is equal to the charge of electron and is equal to the Planck constant and is equal to 1. So it is artificially designed to simplify calculations at the days when people were doing quantum calculations by pen and paper. And it is saves a lot of space on the paper or here on the screen. And there, if one goes to this atomic unit systems, then one gets rid of 1 over 4 pi permittivity of vacuum.
Thank you.
Okay, so now we have nothing but combine all these 5 terms together and be happy. And actually, we are not going to solve any equations. Computer will do everything for us. We just need to be educated what is going on, right? So after we set up position of each atom, we should understand that later computer will build a Hamiltonian that will depend on positions and distances between atoms. So, and we do have 2 types of terms, kinetic and potential terms. And then the natural idea, natural wish of any theorist is to solve Schrodinger equation. As soon as we get a Hamiltonian, one can plug it into Schrodinger equation and try to solve it, or at least to pose a goal to solve a Schrodinger equation. So we have this molecular Hamiltonian. It acts on the molecular wave function that depends on set of all positions of ions and formally depends on all position of electrons. And it gives us some eigenstate. It also reproduces the same wave function. R I R over T sub I. Okay, those are good intentions to solve such an equation. But it is a very rare event to be able to solve it even with all our powerful computers. So it looks pleasant in the shorthand notation, but we should realize that these indices for real molecules goes, I don't know, from 1 to 100 at least, and number of electrons goes from 1 to 1000, even for if you're not looking for some exotic, if you look for like porphyrin molecule. And each vector here has 3 components, x, y, and z component. So we are looking for treating the wave function that depends on thousands of variables. And we get problems in our regular courses just for hydrogen molecule, hydrogen atom, where we have just 3 variables for position of electrons. And it is already a challenging task for a couple of days to sit with pen and paper. If you get thousands of independent variables, it is not a good chance to solve even with most modern technique. So we need to realize that it is ugly. It is an ugly equation. And if we do not need to model real world, if we do not have a request from our experimental collaborators to predict some properties, we would not try to solve it. But since there is a big demand, big pressure, we need to say something. We need to help the experiment to predict properties of materials. We need to find some tricks. We need to find some bypass, some simplest way to simplify this equation. So, is it easy to solve? No. What is difficult about this equation? Many variables. Too many variables. And we should realize that one needs to employ some tricks to solve it. Okay. So the trick number 1 will be so-called separation of variables. So this molecular Schrodinger equation, on the rigorous mathematical language, it is a equation in partial derivative, differential equation with partial derivatives. And the big pain is that it has too many dimensions. So we should hope to be able to reduce the number of dimensions. and we should borrow a technique of separation of variables from the theory of partial differential equations. So the idea is that from one multi-dimensional equation, one gets a lot of one-dimensional equations in the limit, or at least less, well, more equations with less independent variable. Equations with less independent variables. So it would be really great. And as a very little baby step, we would like to at least separate electrons and ions, to be able to solve equations separately for position of ions and equations for properties of electrons. Right now, they are bound together. We write wave function as depending on this long list of positions of both ions and electrons. It would be so great if we could write that wave function is that depends on r, and r small is something like theta depending on r and phi depending on r. This is our wish. This would be great. And formally, it is possible, this trick is possible if each term in the differential operator, if different terms in differential operator depend on independent on different variables. So if we would have terms that depend only on position of ions, and then terms depending only on position of electrons, then one could easily separate the variable and get separate sets of equations for electrons and ions. This would be great. This is a technical goal. But unfortunately, it is not so easy, because we do have a bad guy in our Hamiltonian. Well, not guy, term, bad term. So in our potential for interaction between nuclei and electrons, we do have terms that includes both position of ions and position of electrons. So it is a big challenge. It was partially resolved many years ago, but we should realize that it is a challenge. So there are some tricks. There are some assumptions that in typical realistic situations, there are some features of the material that allow to do this separation of variables approximately. And we are going to learn it next time. This is the big breakthrough in modern science, how to separate the ionic variables and electronic variables. This is not straightforward. It needs some tricks. And the persons who taught us how to do it, their names are Born and Oppenheimer. So our task, or my task, for next lecture is to explain what can be sacrificed to separate variables, to simplify our molecular Schrodinger equation, and refer to achievements by Born and Born-Oppenheimer. So it is called Born-Oppenheimer separation of variables. So I think it will be enough for our lecture number 2. We can revise what we did, and we can make a little discussion if you have questions. So we overviewed what are the goals and benefits of computational chemistry, which are to help experiment, provide some observables, use some theoretical concepts that are already incorporated into software, and they are programmed on the hardware. So we need some input and output. And we started to go through way of converting description of materials into very detailed quantitative way. So we agreed, at least no one was objecting, that we should keep track of positions, momenta, mass, and charge of each particle, of each ion and each electron. And then we combined the information about interaction, about energy of motion of each of those particles and their interaction to each other into molecular Hamiltonian, that in ideal world with infinitely quick computer could be solved and give all properties of any molecule. But since we are limited in resources, both computational and intellectual, we need to simplify the problem. And we are posing a technical goal of separating the independent variables in the molecular Hamiltonian and molecular wave function. So we will try to speak separately about dependence on position of ions and separately about dependence on position of electrons, if we have a good luck. With this, it is the end of lecture number 2, and I will stay here ready to answer any question. If you don't, you are free to leave and enjoy the rest of the day.
Thank you very much.
Thank you.
And Dr. Kilin, it will be available on D2L, like for materials.
Pardon me?
We need materials provided by you, so will it be available on D2L?
Yes, I have an intention to upload these materials to D2L, and if you want, I also can send a bulk email to everyone attending the class.
Sure, sounds good.
These materials are not secret; they are for you.
Oh, okay.
There should be a technology to save all these notes. I never did it before, but I hope to learn it in next 10 minutes. To save my notes and generate a PDF that will have all this handwriting.